just like we have functions which aren't continuous at a point, and we even have functions that are continuous nowhere, we also have many functions that are not differentiable. So it should be clear that if you're not continuous at a point, you're not differentiable there. Let's take a look at this example. In this example, what would the tangent line at C possibly be? There's no line here that could be considered the tangent line at a point C. So, you could think of perhaps this line, but it's completely off if you look at the right-hand limit, right? So hopefully it's clear that if you're not continuous at a point, then you're not differentiable at that point. Let's look at this function and this point. Again, what could possibly be the tangent line at the point C? It's got a slope here, right, and a completely different slope here. So this line couldn't be a tangent line. None of these lines could be a tangent line at C, and none of these lines could be a tangent line at C. So this function is not differentiable at C. And for the same reason, this function isn't differentiable at C. Now I wanted to make it clear that you don't have to, have straight lines in order to be non-differentiable. In fact, I'll make this even more clear. Okay. Again, what would our tangent line at C be? It's too sharp here. Okay. However, if I rounded it off just a little bit, then we would have a tangent line at C. It would be about there. Okay? But the way I drew it originally had a corner there, a sharp corner. So that the slope immediately to the left of C is negative, immediately to the right is positive, so it's not differentiable here. There is no tangent line at this point. Okay. And here the function is smooth, there's no sharp corners, but the slope, I tried to draw it so the slope was infinite here. Let me draw it a bit more clearly that it's infinite. All right. The slope at this point is infinite. And remember, infinity is not a number. So when you have an infinite slope, the derivative also doesn't exist there. So here are 4 examples of functions and points C for which the function is not differentiable. Now, it's differentiable elsewhere. Is the function differentiable at this point A? Absolutely. What's the tangent line? Well, the tangent line is actually the function itself. Here's the tangent line, right here. And is there a tangent line at this point? Absolutely. Tangent line right there. And everywhere else in all of these functions, the tangent line exists. Is there a tangent line here? Absolutely. Here's the tangent line. Okay? So it's just these problem points at C where the function is not differentiable. Now, below these graphs, I've drawn differentiable functions. These are all smooth. Notice there's no kinks, there's no points of discontinuity. Okay, so like I've said before, many of the functions that you know, exponential functions, polynomials, they are all differentiable. But I wanted to talk a little bit about the slopes of the tangent lines. So, for example, the slopes here go from positive, right? Here's a positive slope, positive slope, positive slope, and at this point, the slope is 0, right? And then the tangent line dips down, the slope is negative, 0, and then the slope becomes positive again. All right? And then we can move on to this next function. And the slopes of the tangent lines are quite easy to describe. The slopes of the tangent lines are positive and increasing for this function, right? And for this function, the slopes of the tangent lines are just negative and decreasing. Here they change. It's positive, right? Positive slopes. And right around here you have a 0 slope, right? And then it increases again, positive slopes. So underneath these functions, I'm going to sketch out their derivative. Well, what's the easiest way to do this? Find out where the derivative is 0. So it's 0 here, 0 here. And we know that to the left of this point, the function is positive but decreasing. See, positive and decreasing. Between this point and this point, the tangent line, or the slopes of the tangent line, is negative, right? Negative, 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 but going to 0. So negative, 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 but going to 0, and then the slopes are positive again. So this, if this is f, this would be f prime. Let's draw this one. This one is easy. Let's call this function g. What would g prime look like? Well, it's a positive function because the slopes are all positive. Maybe it's lower here and then it's increasing. So in fact, the slopes of g look a lot like g itself. All right? And let me be clear again. Look at the slopes. The slope is positive, 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 but getting higher. Positive, 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 but getting higher. Let's call this function k, k prime. This is the opposite. These are negative slopes and getting lower. So they're negative and getting lower should look like that. The slopes are negative and getting more negative. And how about this function? Well, at this point it's 0, right? And it's positive and increasing to the right of it, and it's positive and decreasing to the left of it. All right? So let's call this L, this function L, and this is the graph of L prime. So just to recap what these functions are examples of functions which aren't differentiable at the point C. These are functions, and these are the graphs of the derivatives of these functions.